right, good morning, everybody. Welcome to week number 6 in the Geo-Python course. While we're getting started here, as usual, I will remind you, if you haven't already, to please fill in your responses to our poll question for this week. You can see the URL on the webpage that should be visible to you now on the screen, or you can look in the Zoom chat and find the link there. The other thing I want to point out at this moment is that we are recommending that you use the Geo-Python Lite instance in the CSC notebooks this week. We're going to be downloading a bunch of climate data for this week's lesson, and it's been the case in the past sometimes that you can run out of disk space in your regular Geo-Python instance with this data set. So Geo-Python Lite won't have any of the files from any of the previous lessons, but it will work better, I think, for this week's lesson to use Geo-Python Lite. So if you happen to have already launched one of the Geo-Python instances, you can destroy that one and relaunch with the Geo-Python Lite while we're kind of getting up and running and dealing with any of the questions for the material that we covered last week. Okay, so I will try to remind you about that again once we get to the lesson, but that's one reminder at this point. I'm going to now hide my meeting controls, and yeah, let's have a look then at what people have said so far in the quizzes. I'll just once more paste the link into the chat in case you haven't responded yet. So there's a question here about why did Python not recognize the data types of columns before changing the stars to no data? Okay, and yeah, so I can maybe start by saying something about that. Basically, when you read a file in using Pandas, if it finds any character, so like if you have a comma-separated value file like we've been dealing with, let's see if we go maybe here to Jupyter Lab, and if I look at the notebooks for lesson 5, there's not a data file in here, is there? Yes, there's this. So our data file here from last week's lesson in lesson 5 looks like this. It was 30 lines long in terms of the amount of data. It was like a temperature, max temp and a min temp for every day of June of the year 2016. Each one of these things is separated by a comma. And so when Pandas reads this data file in, it will first read whatever the top line is there to try to get the names of the columns. If they have been labeled, it will use those labels as the names for the columns. And then here it's going to expect for each one of these things to find some kind of value that it can assign for each position, each row within one of these columns. If we were to fill in something here that's a non-numerical value, so if we put in, for instance, stars here, especially if we do it in the first row, Pandas, if I understand it correctly and remember correctly, basically looks at the value in the first row of data that it reads in and assigns the rest of the values in that column to be that data type. So if we put in stars here, Pandas is going to try to automatically assign a data type here. It's going to look and say, oh, this isn't a number. It's not a Boolean value. And so therefore it must be a string, a character string. So it would then assign this column for max, for example, to contain character string values and read the rest of these numbers in as character strings instead of treating them as numbers. So it doesn't automatically assign an NaN value because sometimes you have columns that contain text strings and you actually want to have those text values. For instance, if we had a data file that included station names, it's perfectly fine to have a station name, for instance, as a value in one of the columns there, and you want that to be a text string. So the conversion to kind of automatically see it as not a number doesn't happen like automatically, but it can actually cause some confusion sometimes if you have a mix of numbers and character strings in a column, because Pandas is trying to assign the data type by guessing what should go there, but it doesn't always know how to handle it. And that's why we specifically have to say, if you find, 1 star, 2 stars, 3 stars, whatever, treat those as not a number so that the rest of the numerical values will be filled in properly. So that's the reason why the numbers aren't automatically converted to NaN. So we have to basically tell it specifically to treat the character not as a string, like for these stars, but as no data. There's a question about, can I show how problem 4 is done? I can take a look at that in a moment, maybe. But there's a couple other things that maybe I'll talk about just quickly first while we're getting rolling here. So tell something about the final project and what we need to do. Yes, so I can say something about that because I had another question, I think, in Slack, we had a question about the final project. What it will be is it's going to be something that is, it's like an exercise similar to a combination of weeks 4, 5, and 6. So it's not necessarily as much material as all of those exercises combined, but it builds on the material from weeks 5, 6, and 7 of the course. And what we give you in this case for the final project is a notebook where we don't pre-populate a bunch of cells and say, fill this in here, fill that in there, but rather we give you some instructions to do some kind of data analysis using climate data like we've been working with, to produce some plots and to do some kind of calculations, but it's more open-ended. So the idea is essentially to say, now that you've learned these things in the sort of structured exercises, we'll open it up a little bit and let you be more flexible in terms of how you want to approach solving the problems using the Python skills that you've gained. And essentially you do things that are quite similar to weeks 5, 6, and 7's exercises, but with less structure. So the basic idea behind it is that in the past, it's been very difficult for us to assess how much people have actually learned with the way the exercises are working, because a lot of people get most of the points on the exercises, which is great. I mean, we want you to learn and to do well on the exercises, but it makes it hard for us to separate then, like, when it comes to grading, who has actually learned the most. And this exercise is a little bit more open-ended and provides a bit better way for us to assess how things are have gone. When we get to next week, I think we'll talk about the final kind of exercise in a bit more detail, show you what exactly we're asking for, and you'll have a little bit more time than normal to finish that one. Like typically we've given, I think, 2 or 3 weeks time, just so that if you're busy with other things in other courses, you have time to finish the final exercise. So maybe I'll leave it at that for right now, unless there's any other follow-up questions, but that's the basic idea. Okay, so Pandas library is very useful. That's great to hear. And the difference between Ilock and Loc remained a bit unclear. Yeah, this is something that I'm not surprised to see in a sense. So when we introduced it in the lesson, we didn't say that much about Ilock. So if I go here to our processing data with Pandas lesson and just look for Ilock, it's introduced here kind of quickly. So Loc is meant to use the index that's assigned to the data. And what we had in this case is we just had indices that weren't any different than a normal, even like a Python list would have a similar index starting at 0, going up 1, 2, 3, 4, 5, whatever. With Loc, you may have cases where your index is not just an increasing numerical like integer value. It doesn't go from just 0 to whatever, 1 by 1, but it might be something different like a date range, in which case you can select the date range using Loc as your selector. Ilock will be using instead the actual like indexing as if it was a Python list. So it's basically like rows and columns. And so when we select things with Ilock, what we're giving, instead of saying like year moda and temp or whatever, we would be giving like a column 0, column 1, and then row 0, 1, 2, 3, irrespective of what the actual label is that's used in Pandas for that row. So that's the main difference, is basically the indexing looks very similar with the example that we showed, but we'll see, for instance, this week how you can use date time index. And in that case, then the difference with selecting with Loc and Ilock will be a little bit more clear, I think. But the main point here is essentially when you have the I in there, it's meant to do like a kind of typical index selection where it ignores what these labels are for the rows and columns and just says, okay, here's the data itself, and we'll index it down from 0 to whatever. Okay, let's see, what else do we have? I think that's most of that. So there was a question here about problem 4 and how it's done. Let's see, I need to see what problem 4 looks like and remind myself so that I can say whether or not we have the way to show how that's done. Yeah, so we were doing data aggregation. We're going to cover that in this week's lesson. So I think maybe I will not demonstrate how to do that right now, but rather introduce it when we get into the lesson materials, because that's one of the main things we're going to cover today, is taking things like hourly temperature observations and condensing those down to like a monthly average using data aggregation and grouping in Pandas. So problem 4, after you see today's lesson, will probably be fairly clear how to handle it. But we just put this in there as like a fun example if you wanted to look ahead and read something on grouping, that you could have that opportunity. So I think that covers the kind of starting everything up questions. Unless there's anything else, maybe if there's any other questions in chat or something like that, you could say something there. But otherwise, if not, we have a sort of busy lesson today, so I think it's probably good that we get moving. One more time, I'll just remind you, if you haven't already, to open up one of the CSC notebook instances for the Geo-Python Lite for this week, rather than the regular Geo-Python. Because of the data we're going to be downloading, it's best to use the Geo-Python Lite instance. Okay, so what are we up to this week? Well, we're going to continue with Pandas for the first part of the lesson. And then after that, we're going to talk a little bit about things that are more kind of programming concepts related to resolving error messages, using something called an assertion in Python to make sure that the values your code is using are working as they should. And then finally, a little bit about debugging your Python code before we get to the preview of the exercise. So I'm going to go over here to my CSC Notebooks instance, go to Notebook lesson number 6, and then it's the advanced data processing notebook that will open up for today's lesson. And I'm just going to, maybe leave it like this. Maybe I'll make this a little bit bigger if I can zoom in. Doesn't want to zoom in for some reason. Okay. Maybe make it one more click bigger and hide that for right now. All right, so in our lesson for this week, essentially we have a motivation that comes from April of 2019. This is looking at global temperatures and the kind of global temperature departures, which we'll call anomalies after this later on in our lesson that we're working on. But what you can see just looking at this map essentially is how much warmer it is, if it's a kind of white to red color, how much warmer it is than the average temperature for April over some reference time period. And if you look here in sort of parts of Northern Europe, for instance, over here, you'll notice that we're in the full-on red, quite warm, quite a bit warmer than average color range. And as it turns out, there were 13 locations in Finland that had their warmest April on record in the April of 2019. And there were many other places in Europe that had similar trends. Our goal for this week is to basically look at the data from 15 different weather stations in Finland. And to do this kind of assessment ourselves based on the weather data, to calculate what the average temperature is in April for all of the years of our data sets, and then sort them so we can see which years were the warmest on record from all of these different stations. In order to do this, we're going to have to do a number of things with Pandas. So we'll be doing some renaming of columns, which I don't think we covered last week. We're going to do some iteration of data frame rows and applying functions. So this is another thing. We did some calculations last week to calculate a temperature, but we didn't apply any functions in last week. So we'll show you how to apply functions to your data in a Pandas data frame. The data aggregation thing will be basically where we take our hourly temperature data and condense it down to monthly average values. And then we're going to repeat the task for several input files. So that's where we're kind of going. And the input data is very similar to what we've been working with in some of the previous lessons and exercises. It's climate data from the National Oceanographic and Atmospheric Association in the United States. So they've got a nice database with a lot of easily accessible data. And depending on which of the instances you're using, you'll either have 15 stations or 4 stations, just to not totally fill things up. So in this case, because the data is pretty big, we didn't include it in the notebooks that are automatically available here in the CSC notebook system. So we need to download the data, and that's our first step. So I'm going to assume that most everyone's using CSC notebooks. I wouldn't recommend using Binder for this exercise or for this lesson. Binder's not going to work that well. And yeah, for those who are using CSC notebooks, what I'm going to do is just demonstrate how to download the data. If you're using something else like your own computer, you can also find instructions on the course page in this lesson about how to download the data to your own computer, but I'll demonstrate it here for the CSC notebooks users. So the first thing we need to do is open up a terminal window. So you can go up here to File and to New, and then you can select Terminal from the menu here. If you click that, it's going to open up a new tab. And what I'm going to do, and you can do this if you like, is just drag this, like click on the tab, drag it down here and put it at the bottom of the window of what I can see, because I want to be able to see what the instructions are here in the notebook we're working in, plus the terminal at the same time. So first thing is we need to go into the directory where we want to download our data. And that's the notebooks L6 directory. And we can change directories in this terminal by typing CD and then notebooks. And then the /L6. And if you hit enter, you can now type LS in the terminal window and you should see these notebooks. So our advanced data processing with Pandas, debugging, errors, and then the assertions notebook, and then there'll be an image and metadata directory. So you should see that kind of stuff. If you're not seeing that, maybe say something in the chat so that Hovard or one of the course assistants can give you some help. So if you type ls and you're seeing these files, it means you're in the right directory, which means you can then just highlight and copy this line here where it says wget blah, blah, blah. So we're just going to copy and paste that into the terminal window here. Wget is just a simple program for downloading things from a web page. So here in my personal GitHub repository, I have a data directory where I've put this data file, and we're just going to download it from that location. So if you type wget and then, or just copy paste this thing and hit enter, you should see that it downloads fairly quickly, and you end up with this data file now that if you type ls once again, you can see Finland weather data full.tar.gz as the file name here. That is an archive of files in a certain file format. It's compressed, and um, in order to actually use the data, we now need to extract it. And to extract the data, what you can do is type tar and then ZXVF. In case you're curious, it's unzip, extract. V is for verbose, so it shows the files as it does it. And then the F here is saying that the next thing you give is a file name. And so then after that, you can type Finland weather data full.tar.gz. Once you've typed that in, if you hit enter, you'll get these little whatever shilly messages that you can ignore. Don't worry about that. But this will extract the data file such that if you type ls at this point, you should now see you have a data directory that is here in our lesson 6 folder. What I'm going to ask you to do is, if you could, once you have completed this, you can go to the, I think it's in the reactions option in Zoom and put a green check mark. That way I can know that everybody has successfully been able to download and extract the data files. So please, fill in the green check marks, and we'll pause for just a moment while people are getting their data downloaded. I'm going to go back here to the file browser in Jupyter Lab. Over here on the left side, you can now see that there's a data directory that was not here previously. And when I double click on that, here are the data files that we have for this week's exercise. So there are, I think, should be 15 of these files like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, there's 15 of those. And then there's 3 files here that describe the data. These are metadata files. So for instance, in this 3505 doc, this basically tells us what all the different columns are in the data file. So it explains then what these abbreviations stand for. So like USAF will be one of the columns. It's Air Force Catalog Station Number, and so on and so forth. So this is metadata about the format of the data files. Then the one here next to it is showing us, it doesn't show up quite that nicely because it's getting wrapped. The line is getting wrapped here, but it shows for which stations we have. So this is a station number, then Sodankula, for example. And in this case, we have data starting for the first year, it's in 1917. And then this is each month, how many observations are included for that month. So you can see right away from this kind of summary of the data that, for instance, in, I guess, January, February, March, April of 1918 in Sodankula, there were 0 observations. So maybe there was a problem with the data that was being stored. Something went wrong. But yeah, this is another kind of description of what data we have in the archive that we're working with. The last file here, and I see there's a question in chat. I'll come to that in just a second. The last file here, again, is another kind of summary, and unfortunately doesn't look so nice in here because it is wrapping the lines. I think maybe there is a way to turn that off. So if you go to View and click Wrap Words, that will turn off the line wrapping so that the long lines here, for instance, like this, don't get wrapped around at the end of the page. So this shows us then, again, these are the station ID, the name of the station, which country it's in, oops. And then over here, longitude, longitude, latitude, and elevation. So this is just information about the station positions geographically. So that's our data that we have. To this question here, am I supposed to have green, blue, and red text at the end after using the tar ZXVF line? What does that mean? The 2 baselines. I think I don't think I've done anything special with setting up the environment here. So yours should basically look like this. If everything's gone well, first off, the wget command should produce this file in your working directory. When you run the tar command, if everything goes well, then you should get this data directory. That's kind of how you can know things have gone as expected. So if you're not seeing the data directory, or if you don't see this file, then what you need to do is go back and run this wget command to download the file. And then after that, once it's downloaded, you should be able to run this tar command. Finland weather data CSC. Yes, so sorry, it should be this one here. Finland data weather data full.tar.gz. So maybe if you were looking, there are two different data files, and there's instructions for the Geo-Python Lite and for the regular CSC notebooks. Maybe you downloaded the file for one and then use the command to extract it from the other. So just pay attention. You want to use the wget command and the tar command from the same section here under the Geo-Python Lite blueprint. If for some reason you've downloaded the wrong file, you could just type rm and then the name of the file. So Finland weather data full.tar.gz. So you can type that if you're having, like, if you've accidentally downloaded the CSC notebook file for the regular GeoPython instance. So that one is listed here. Its file name will be Finland weather data csc.tar.gz. Sorry for the confusion, but there's a kind of a, this data file is the Lite version because it's smaller, but of course it doesn't go with the GeoPython Lite instance, so it's rather confusing in the namings. Apologize for that. But yeah, if you've got the wrong file, you can just type rm and then the file name, and you'll see that the file goes away. I don't need the data file anymore because I've extracted the files from this archive already. So you can also delete that if you want, but it's not necessary. But the point is that if you type ls data and hit enter, you should see a bunch of files listed there if everything has gone well. If not, maybe send a direct message to Håvard and hopefully he can give you some guidance. Okay, at this point, I'm going to drag my terminal window tab back up to the top and switch over to the notebook in kind of full screen view, and I'm going to hide this file browser for right now. All right, so we've got the data, hopefully. About the data, yes, I've already kind of walked you through a little bit about like what the data files are here. So there's listed stations, details about the observations, and then the data description. Those are the metadata files. And if we look at one of the data files themselves, for example, our format looks like this. So in this case, we don't have comma separated values. We have a data file where the values are separated with a fixed column width. So there's variable numbers of spaces between the columns depending on which values are reported there. That's something we haven't dealt with yet. So that'll be one of our first challenges, is reading in this data file. Otherwise, you can see there's a bunch of things here with somewhat confusing headings for the different columns. Probably not immediately obvious what all of them are. Temp, I guess you can probably figure out as what that one means. And similarly, there are some things here like SPD for wind speed, and then here you can tell this is going to be something about a date. But yeah, we need to start out here in our lesson for today by reading in this data from one of the files. We'll start that way, and then we'll show you at the end how to kind of batch process things. In order to start, of course, we need to import pandas. So let's do that here. So import pandas as PD, and you could just shift enter to run that cell. We had a quick look already at one of the data files. The one we're going to load first is this 029440.txt for the Tampere-Pirkkala station. And yeah, with reading this in, as you saw, we have different numbers of spaces there. And there's actually two different ways you can handle that when you read things in Pandas. We're going to use the option here called delim whitespace, which indicates that the white space or the space between the labels should be used as a delimiter instead of a comma, for instance. So we'll say delim whitespace equals true when we read the data in. And as we saw before, our NA values are going to be different numbers of stars. And so we'll also list that when we read the data file in. This is already filled in for you here, just because typing it in is kind of clumsy. But our data file that we're going to use here is the data 029440.txt. And then we're going to delimit with the white space and use NA values with different numbers of stars. So I'm going to run that cell. Should take just a moment. I don't remember how many lines are here. Looks like there's a little warning message, but this should be okay. I think it's just complaining about mixed data types in certain columns, and that's not a concern of ours because we're going to reread our data file in just a moment and get past that issue. But if we type, for instance, now data.head, because we read our data file into a variable called head, you can now see what looks like our data from the text file that we saw before. So we see our different columns. Here's our dates. Here's our wind speed. And if we kind of go along the side, we would see further over to the right some of the other values, like temperature. This all looks fine, 33 different columns. I think that's what was expected for the data file that we're dealing with here. And if we want to just check and see what those columns are, you can type data.columns and run that. And what you see here with the data.columns is all of the column headings, and those look very much like what we saw in the data file the first time when we read that in. So, or first time when we saw it in the kind of text preview. So these look like the same kind of headings that we had before. You'll notice that the MW, there's now an MW 0.1, 0.2, 0.3. That's because they had the same name and the column headings have to be different. So I think Pandas is automatically adding in this kind of 0.1, 0.2, 0.3 stuff. So yeah, we're going to read the data file in though once again, because there's 33 columns of which we really don't need that many. We're going to keep some of these. We'll keep the station ID. We'll keep the date. That's useful. We'll keep the wind direction, speed, and the wind gusts. And then the temperature and the max and the min temperature. So we'll just basically do the same thing we did before. We'll reread the data file here, delim the white space like we did previously, use the NA values like we did previously, but we're going to now use this use calls parameter to tell we only want certain columns out of this data file, not all of them. Again, this is already here for you just to kind of speed things up. And now if you read it in again, you'll see also at the end of this code cell, it has data.head. So it now prints out what the data looks like in the format now when we've reduced the number of columns so we don't have things that we don't expect to use. Okay. Everything looks pretty good at this point. What we can do, though, is we can still improve dealing with our data a little bit. We've trimmed away a bunch of columns we don't need. That's great. But we can actually also go through a process of renaming the columns. So Pandas will automatically take whatever the headings are that are in your data file and use those as your column headings, but they don't always make sense. My personal favorite is this your moda her column for the date. That's one that's not particularly useful, and it's a pain to type that in if you want to use the date. So we're going to rename them to simplify things. First off, we can just do a quick data.columns to see all of our column names. So data.columns and run that. You can see here we have these, I guess, 7 or 8 different columns that are mostly okay, but some are not so useful, like temp is not going to be too bad. but we'll rename these, and the way we'll do it is we're going to use a Python dictionary. And a dictionary is kind of a nice little structure in Python that allows you to relate a key to a value in a pair. And I'll show you basically how that works here by creating a dictionary to rename our columns. Okay, so let's start out with making the name of this dictionary, which we'll call new names, be our new column names. Just doing this like a normal variable assignment. The thing is, you indicate a Python dictionary by wrapping your values in these curly braces. So at least for me on a Mac, this is Shift Option and then 8 or 9. For the parentheses, I guess it would probably be like Shift Alt for Windows keyboard to get the curly brace. And the curly brace here, then we will say, we can list a set of these key value pairs where you have a key, a colon, character, and then a value. And our key, for instance, could be YR dash dash mo da her m, right? So year, month, day, hour, minute. And that's in quotation marks because it is a character string. Then after that, you put this colon character, and then we're going to rename this time. So then we can just put time like that. So this would be a single entry dictionary where it would take and find a value here by the key this, so your, mo, da, her, and it would return then time as the value that's associated with that. I guess maybe you can already see a little bit of how this is going to work. So now we can put a comma, and we'll do a few others. We can take, for instance, SPD, and rename that as speed. Might as well give it a little bit more clarity in the name. And similarly, we can take Gus and rename that as Gust. Now, at this point, all we've done is set up this dictionary that will allow us to rename our columns. We haven't renamed anything yet. You'll notice like data is not in here anywhere. We're just making this dictionary. So once you've created it, we can type new underscore names down here. And if I run this, I see basically the same output that I've typed in above. Here's our year, mo, da, her, and it's related to the value time. Our key SPD is related to the value speed, and our key Gus is related to the value gust. And if we check its data type, like if we just type of new underscore names, we have a new data type we've not yet encountered yet, which is a Python dictionary. So there's a little bit more information you can find out about dictionaries up here. They're very useful. I use them, not all the time, but periodically, and they're kind of a very nice way to solve certain kinds of problems. So if you're interested, you can look in the blue box here and find some more information about Python dictionaries there. For the moment, all you need to know, I think, is just how to create them to do this kind of renaming of the columns type of operation, which is now what we can do next. To do this, we're going to use a function called rename. So we'll say here that our data equals data.rename. And then for this, the parameter it's expecting for this situation is columns equals, and then new underscore names. So this is going to rename the columns using this dictionary called new names. So any place it finds a column with this key, like year, mode, da, herman, or SPD or gust, it will then replace that with the value time, speed, or gust. So if we run this one and then print out our data columns, that's what's going to already be in the text in the cell that's here. You see now we have USAF, time, dir, speed, gust, temp, max, and min. Much better than what we had previously. And now you have a chance to test things out yourself. So as you can probably already guess, we're dealing with temperature data that is in temperature in Fahrenheit, and we are most probably going to want to work with Celsius, as that's a more familiar temperature scale to most of us. And so we're going to need to rename the temp column to temp F just to avoid any possible confusion about what unit is associated with the temperatures in that column. And in addition, you can rename the USAF to station number. So you've got a little box here where you can do that and basically follow the same kind of instructions that we had above to do this kind of renaming of a couple more of the columns in our data frame. And when you're finished, you can put a green check mark, and then we'll continue from that point. Okay, well, there we go. 17 green check marks, 18. Perfect. Yeah, so we had this task to rename a couple columns. First off, we had to make a dictionary for the new and old names. So we can do that just like we did before. You can call it new names or whatever. You can, doesn't really matter. We're going to overwrite what's in that variable as it is. So why not just call it new names? Then we got our curly brackets. And again, it should be now key and value. So we want temp as the key, and the value we're going to replace that with is temp underscore F. And then we were also going to rename at the same time our USAF to be station underscore number, like that. That is our new dictionary. Then to rename the columns, we'll just say data equals data.rename, as we did previously. And in this case, we'll say columns equals new underscore names, just like that. If I run this, the data.head is already there to show us what the output looks like. And here now we have station number, time, dir, speed, gust, temp F, max, and min. Looks great. All right, perfect. We can continue then on to taking a look at our properties of our data at this point before we get into the next step. We can first look at data.shape to see how many rows and columns we have in this data file. All right, so we probably already had a pretty good sense that we had 8 columns. We've seen those column headings and changed some of them already. But in terms of the number of rows of data, we have quite a bit of data in this case. So we have 750,000 plus lines of data, or 750,000 plus temperature observations. So we're dealing with bigger data files this week, as you can probably tell. We don't have 30 lines, we have a lot more. Data.head, as this data file is sorted already by the date, tells us when the sort of observations start. So you can see the first one here from 1906. At the first of the year at 6 in the morning is our first observation in our temperature data set, and data.tail. If we run that one, gives us the last observation. So the last observation in this case is from 2019, from October 1st of 2019 at 11:50 p.m. on that day. So that's our head and tails. So you can see basically how much data we're dealing with in time. The data types of the columns we haven't looked at yet, so we can do data.dtypes as a reminder to check the data types that we have. So station number and time are both integers. If you look at this, it makes sense. Station number is an integer value. Time is also, in its format here, an integer value. And the others then are floating point values for the other columns. So no big surprises there. And if we do data.describe to see our descriptive statistics, you can see a bunch of things here. So mean values, standard deviations, mins, and different quartiles and things like that. What you might pay some attention to here is the count column. And the reason for this is that the count column tells us how many data values do we have in each one of these columns. So for the station number and time, we should expect to have all of the observations there. Because the time is reported here in scientific notation, you get a little bit different looking format, but it's 7:57, 9:83. And this is 757,983 times 10 to the 5. So 7.57983 times 10 to the 5, which is the same number there. That's the total number of observations we have. But if we look at the wind direction and wind speed, we have different numbers there. For the wind gust, we have far fewer observations, only about 20,000. And for the temp, we have most of the observations, 754,000. So there's still some missing. But then for max and min, you can see there are many fewer values reported for those columns. So that's something good to check with this descriptive statistics when you want to look at your data file, just to get a sense, how much data is missing, how many things are just not present there in the data file. So that's a handy thing to review. Now we can go into doing some of our conversions. We'll convert our temperature data now from Fahrenheit to Celsius as a typical step that we've been going through in many of the data files we've dealt with. And we'll do that first by creating a function to do this conversion. We've already created this kind of function before, so we're not going to make you type it in again. We'll have a function here called far to Celsius that accepts a temperature in Fahrenheit and returns a converted temperature in Celsius. And of course, the function calculation that happens here is the temp Fahrenheit minus 32 divided by 1.8, which is 9/5. And that gives us our converted temperature. So just run that cell, and that'll define the function. And if we want to just test it out to make sure it's working properly, we could do, for instance, far to Celsius. And if we give it 32.0 Fahrenheit, that should be 0 Celsius. And if you run that, you should hopefully see that you get a value of 0 back. Now, I'm going to run data.head one more time here, just so we can see again what we're looking at with our current data frame at this point. And the first thing we'll introduce here for how to use this kind of function is to do an iteration over the rows of the data frame. So this is going to start at row 1 and just go through sequentially each one of the rows and do some kind of calculation. The format of this looks a little bit like a for loop, but it's kind of slightly modified. So here we have the for that would normally start a for loop, but now we have two values separated by a comma. So idx, comma, row in data.iter rows. So this is something that is going to come out of Pandas from this data frame. What we'll do is we'll start up our for loop, we'll print out the value of index, we'll print out temp f as the value at whatever row we're in currently, temp f, and then we'll add in here a new line character. I suppose I could have done these as f strings, but missed that one when looking at the exercise or the lesson. And then we're going to have a break. So a break statement basically will, if you're in a for loop, for instance, it stops and bails out of the for loop at that point. We're going to print out one value essentially and break out of our for loop. So I'm just going to run this. After one iteration, it hits the break statement and stops iterating. So you know that there's 750,000 rows in this, 750,000 plus rows in this data file. So we could get a lot of screen output, but we just wanted to check and see what is the index and what is temp f with a simple statement like this. By adding the break in there, it just stops our loop and only displays one thing. So we can see here, for instance, that index is 0 and temp f is in fact the value of temp f for row 0. So the index is going to be the index of which row we're at in the data file, and row is then going to be containing all of the data from that row of the data frame. So if we look at here, here's our index 0, and then the row would contain these values from the first row of the data file. That's how this iterows thing is working. So for idx, comma, row in data.iterows, do some stuff. Okay, so if we want to do something where we're going to fill in a value of a new column called temp C, we can first create that column. So we'll do that here. This is already filled in for you as well. So data temp C equals 0.0. We did this last week, so there's no need to kind of rehash having to type this in. And what we'll do is we'll say for idx, comma, row in data.iterRows, convert the Fahrenheit Celsius to temperature. So we're going to take our Celsius value and assign that the far to Celsius of row temp f. So that will take the temperature in Fahrenheit in a given row, use our function far to Celsius to convert it to its Celsius value, store that as a variable called Celsius. And then we say data at idx. So at this location, at this row of our data frame, in the column called temp C, fill in the value that we just calculated for Celsius. This is a for loop, so every time it goes through, it's going to get a new value for temp Fahrenheit, convert it to Celsius, and fill it into a new location in the data frame. So it kind of just goes through from the top to the bottom, tick, 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 filling in all of those values. Whoops. Okay. So if you run this, it might take a moment because remember, there's about 750,000 columns or rows rather to process. So you'll see this little star here for probably 30 seconds or so while it goes through each one of those and does this calculation. And while that's calculating, we can just remind you about the data.at versus data.loc. So remember, data.at will be used to refer to a specific row and column, and data.loc is often used to refer to a range of rows and columns. And what that means is that if you're filling in a value to a single spot in your data frame, data.at is generally faster because data.loc is designed for a slightly different purpose. We could use data.loc, it would just be a bit slower to do the same calculation, whereas data.at is a bit quicker. At least for me, this is now completed. And if we now want to take a look at what our data frame looks like at this point, we can do data.head. And you should hopefully see there's a new column called temp C. And if we look over here at the temperatures in Fahrenheit, they're below 32 degrees, which means they should be below freezing. And these look to first order about right for the expected temperature values in this case. So it does appear that everything has worked properly. So this is fine. This is one way we can do things. Iterating through, sometimes you need to do that, especially if you're doing something kind of like that depends on the value from the previous, like from the row above you or something for some calculation. Maybe you want to iterate through and do things that way. But it's not the fastest way to do things, especially when we have a simple situation like taking all of the values in the column and converting them with the same function. We can use a different approach, and that is to apply a function. So if we take our data and we just take our temp F column, this is our temperatures in Fahrenheit, and we do dot apply, and then a function name, in this case, far to Celsius. This is the way in which you can apply a function. So here, you don't give the parentheses when you give the function name. It's sort of expected that whatever needs to go into this function is listed over here on the left. So here we have a single column value, a single temperature, column of temperatures, and then each one of those temperatures will be given to this far to Celsius calculation. And if I run this cell with data.apply, what I get back is all of the temperatures now converted from Fahrenheit to Celsius. They haven't been stored. This is just printed to the screen at this stage, but it's just so you can see how it works. Now, you remember when we did this data.iterRows thing just above, it took about 30 seconds or so to fill in the temperature values that we were converting from Fahrenheit to Celsius. Let's now do the same thing, but we can use our apply approach. So we could say here that our data, and let's call temp underscore C. So we're going to overwrite the values that we just filled in our temp C column, equals, and I'm just going to copy this from above and paste it here. So this is our data temp F dot apply far to Celsius. This is doing the same calculation we just did with iterRows, but we're going to apply our function this time instead. run this, and it's already done. So this is much faster, which is the reason why, generally speaking, if you have functions to apply to your data to do some kind of conversion like this, it's recommended to use this .apply approach. It's far more efficient. However, there are some cases where you just simply need to do the iter rows approach to be able to do things, and that's perfectly fine too. It's a matter of, sometimes you need to find the right tool to solve the problem, and that's more important than how quickly the solution is produced. One other thing to note here is we could do this for several columns at once. So we could take our data, for instance, I've got to do this as a second set of brackets here. So we're going to list some values in here. So before, like when we were trying to deal with having multiple columns, you have to have inside of the square brackets another set. And let's say temp underscore F. And let's go with max and min. So we can take all of those and .apply and far to Celsius. And again, here you see that we're not assigning anything to the data frame. We're just running this just to show you that you can do this in multiple columns at once. And if you do that, okay, most of our max and min values are nans right now, so you don't see that they have been converted. But the point is, yes, they have for the actual cases where there is a numerical value, and you can see that in the temp F column pretty clearly. All right. Once again, it's now time for you to check your understanding, and you can do that by converting temp F, min, and max to Celsius by applying a function just like what we did above. And you can store the outputs to temp C, min C, and max C. And you can go ahead and do that here in this empty cell underneath. And what I will do is clear away the old responses. And once you've done this, I'd ask that you put a green check mark to indicate that you've been able to complete this task. And we'll continue in just a moment. Okay, it looks like maybe still a few people are finishing this up, but I'm going to go ahead and move forward just because I don't want to risk running out of time. So yeah, basically what we did above was exactly this kind of conversion of temperature in Fahrenheit for the temp F, min, and max columns to temperature in Celsius. That's what we did here. So I'm going to copy this and paste it down here. So we know that that's what we want to have output, and what we need to do in terms of our data frame to store it is we need to then say that our data, and again, double square brackets here because we're going to list some columns. So we could say temp underscore C, max underscore C, and min underscore C equals data of those corresponding temperatures in Fahrenheit .apply far to Celsius. So it's really very similar in this sort of format here. We list some different columns to apply the function to, and then we list another set of columns where the output should be stored. We run that one and then do data.head, for example, just to take a look at the columns we have. You can see now we have temp F, max and min, and temp C, max and min. So our temperature values have been converted as expected. There's a little blue box here about the iter rows versus apply. We already talked about this, that apply is often more efficient, and that's that. All right, now our next topic here is about parsing dates. So we have our column with our year, month, day, hour, minute values that are already in there. And for instance, if we type data rather, and let's look at the column is now called time. dot head. And just as a reminder, if you put a number in here for the dot head, you can get whatever many rows from the top of the data frame. So if I put head 10, then I get the first 10 rows here. And if I just copy this down below and change head to tail and run that, I get the bottom 10 rows of the data frame that way. So you can see here, the first 4 digits are for the year, then we have 2 for the month, 2 for the day, 2 for the hour of that day, and 2 for the minute of that hour. Pretty standard data format for this kind of thing because there's a constant width. Unless we reach the year 10,000, then things are going to get more complicated. But at least until we get to the year 10,000, there's always going to be 4 digits for the year, 2 digits for the month. So if it's a single digit like July, where there's only the 7, it would be as 07. And then the same goes for the day. If it's the first, it would be 01. So that's always 2 characters wide for the day. And again, this is an integer data type as we saw before. So for instance, if we just took data time dot dtypes and ran that, we'd see the data type for the time column is an integer with 64-bit precision, as we have previously seen. Well, what we're going to want to do here is we're moving in the direction of doing our data aggregation step, which means we're going to be condensing our observations we have now here. If we take a look at our file, we can see we have something from 6 a.m. on the 1st of January in 1906. Then it looks like it's 1 p.m. and then 8 p.m., 6 a.m., 1 p.m., 8 p.m. So I'm just looking at the last 4 digits here. So it looks like in 1906, there was about 3 observations per day of the temperature. By 2019, things have changed a little bit. So here we have 2050, so 8:50 p.m., then 9 o'clock, 9:20 p.m., 9:50, 10 o'clock. So about every 20 minutes or so, 10 to 20 minutes, depends a little bit. Interval is not exactly constant in those. But here we have multiple observations per hour, whereas previously we had only 3 per day. Regardless of that, we want to be able to condense these down to, for instance, a single value for the month of April, as an example. And in order to do that, we're going to use some steps here in our data frame that will allow us to easily group together all of the temperatures from a given month of a given year to be able to calculate an average. Our first step toward doing that is to convert our time values into a character string from what they are right now, which is this integer value. So we can do this as data, and let's call it time underscore str to indicate that it's our time in a character string format. And this is equal to data time dot as type str. So we saw this last week, how to convert from one data type to another. In Pandas is just to do this, as we're showing here, to convert to a character string from an integer. So run that one. Now we'll have a time column that is a character string. And the reason for doing that is we're going to take advantage of something called string slicing to chop up this character string and get only the year and month out of it. So what we have, for example, here, if we consider one of our dates, let's just say date equals, and let's grab this one here, the last day of our observation, which is 2019 on the 1st of October at 11:50 p.m. So if that's our date, we can do our string slicing, for example, by saying, if we look at date 0:6, this is going to give us, from this character string, the value starting at character 0 and up to, but not including the character at index 6. So it'd be 0, 1, 2, 3, 4, 5. So we should get 2019 10 for the month of October. when we run this cell like that. So we get 2019, 10. Someone's notebook stopped working even after they restarted the kernel and run all cells. It still doesn't work. Okay. Hovard, I don't know if you're available to do some tech support, but maybe you can help. Bart seems like, yeah, maybe there's, yeah. So hopefully Hovard can help in the chat. So we slice this string to take only the first 6 characters out of it, which is, as it turns out here, the year and the month, and we just dropped the date, the hour, and the minute. This is basically how we're going to approach this problem of trying to group things together on the basis of which month of which year it is. So this is how you would do it for a single string. You just have your date as some character string here, and you just take a certain number of characters out of it. But we can do the same thing with our date in Pandas by doing the same kind of operation here. So if we say, let's give our data frame name, so data, and let's say year underscore month. This is going to be a new column that we store for the year and the month, equals data, and now we'll take time str. And now I'm going to show you the way to do the string slicing in Pandas in a column of value. So it's now str.slice, and start equals 0, stop equals 6. So this is basically doing the same thing that we did above for a single value, but now doing it to an entire column of values out of a data frame in Pandas and storing the output in a new column called year month. So if we run this and then run data.head, what you'll see is now we have a year month column where we've taken and basically taken our date values, but dropped everything except for the year and the month. The reason this is helpful is that we can now, in the next stage, group all of the values that have the same value here for year and month together, which means that every temperature observation from 1906 in the month of January can be easily located and grouped together to do things like calculate the mean temperature for that month. So we have a check your understanding opportunity here and create a new column called month with the information about the month without the year. I think in the interest of time, I'll just show you how to do this one because there's some other things we should move on to before we run out of time. It's not really that much different from what we did above. In fact, what I'm going to do here is copy this example and just modify it because it's easier to do that way. So if I paste this in here, we want our task with creating a new column called month. So I'm just going to delete the year part of this. So data month equals data time str, and then str.slice, starting here instead of at 0, because that would start in the year, I'm going to start at 4. So it's, again, position 0, 1, 2, 3 would be the year, and then 4 and 5 are going to give us the month. And so if I run this, that should create the new column. And if I do data.head at this point and run that, we're getting a lot of columns here, but now you can see just the month isolated in that way. That's a handy thing in cases where you, for instance, want to group all of the January observations together to say, like, what's the average temperature in January from all of our data that we have? Not just a single year, but for all years in the month of January, what is the average? You could do that now by grouping by this month, for example. There's a little bit here about date time that follows this. We're not going to heavily use the date time indexing, but this is one of the things in Pandas that's really powerful and kind of fun and interesting to play with. But I will leave this as something that you can kind of look through. The basic idea here, I'll just kind of click through and run these cells, is that we can convert our data from something like a character string that we have for our time currently to a date time object in Pandas. So if I just run this cell, it takes a moment for it to do the conversion because it has to parse all of these character strings and convert them to a date. But instead of being stored as just like 190610010600 or something like that, which is kind of, once you know the format, not horribly unintuitive way to look at the date. We can do a little bit better, and that's what the date time is meant to do. It allows you to do certain operations much more easily and to read dates and interact with dates more easily. So if we look at our data.date column.head, you can now see that the year, the month, and the day are sort of split off in a different way, and you can also see the time reported in a little bit more intuitive format. The benefits of things like this is that if we want to know just what year it is, we can take our date.dt.year and run that, and we immediately get back just the year of the date, or date.dt.month. If we run that, we get just the month back, so it's quite handy. And then you can sort of start stacking these things together, like saying data.date.dt.year.n unique. So this will give us the number of years, of unique years that are in the data set. And so here we can see we have 51 years of observations. So we started in 1906, we ended in 2019. Obviously, there's some missing time in there, given we only have 51 years of unique observations. So there must be some block of time when there were no observations reported. And in addition, we have things like, what you can do is the same kind of step that we did above, using the date time, do these kind of conversions where you convert to a string with a certain format and store that in a year and month in the date time format. So here you have to give this format parameter with how you want to store the date. So here's %y would be for the year, and then %m for the month. And if I run that and then take a look at what's in that column, what it's done is it's basically just dropped any of the day values here. So it just assigns everything the first day of the month. So this is kind of like what we were doing with the string slicing, but using the date time. Again, take a look through it. I just zipped through this very quickly just to demonstrate for you. But I think at this point, probably we should take a little break. We have a couple last steps left where we're going to aggregate our data, which means essentially we're going to group things together by the month. And then we'll show you how to do this for all of the months. But I think at this point, yeah, we should take a 10-minute break. Are there any questions before we go for a short break? Okay, so if not, we will continue at, let's say 10:50. So that's about 10 minutes from now. So we'll continue in 10 minutes, and we'll start by aggregating our data when we come back.